The Panther's frontal glacis plate didn't just fail, it shattered. Normandy, July 1944. A British 17-pounder fired from 800 meters. The armor-piercing shell struck at 40 degrees, non-penetrating by every calculation in German test reports. But the 82mm plate didn't deflect the round. Instead, a 1.5 meter crack ripped along the primary weld. Inside, the driver watched metal fragments, his own tank's armor, explode backward at lethal velocity. The shell never entered the crew compartment. The crew died anyway. This wasn't an outlier. Soviet testers at Kubinka, firing at a captured Tiger II in August 1944, documented this same phenomenon repeatedly. When armor was not penetrated, the armor formed large cracks, and large fragments broke off the rear side. American metallurgists examining a Panther glacis plate in January 1945 used different words for the same failure: poor toughness, rough crystalline surface, inferior shock properties. Something fundamental had broken in German steel. But the killing mechanism that exposed this flaw wasn't kinetic penetration, it was thermal metallurgical violence traveling at 25 times the speed of sound. A copper jet compressed into a needle-thin stream by explosive force, striking armor with pressures exceeding 100 gigapascals, temperatures reaching 700 degrees Celsius at the impact point. The metal didn't need to melt, it needed to fail. A Panzerfaust warhead weighed just 3.5 pounds. Its effective range barely exceeded that of a hand grenade, 60 meters for early variants, 100 meters for improved models. Yet by spring 1945, these disposable tubes accounted for 1/4 of all Allied tank casualties in Europe. Production had scaled from 40,000 units per month in October 1943 to 1.5 million monthly by war's end. Stay with this story, because what you think you know about melting tank armor is wrong, and the truth reveals a collision between desperate innovation and catastrophic industrial failure.
The Third Reich entered 1940 with metallurgical confidence and geopolitical desperation. Germany's tank armor, face-hardened chromium-molybdenum steel, had performed exceptionally in Poland and France. Krupp's specifications called for precise alloying: 1.67 to 2.30% chromium, 0.20 to 0.30% molybdenum, carbon content below 0.34%. Burnell hardness ratings of 250 to 300 provided optimal balance between penetration resistance and structural integrity. Quality control mandated that each factory batch undergo ballistic certification valid for 2 years. Failure rate, less than 5%. This was engineering aristocracy. Then Operation Barbarossa revealed the T-34. Soviet armor, appearing in quantities German intelligence had catastrophically underestimated, rendered the Panzer III's 50mm gun obsolete overnight. The strategic response, up-armoring and up-gunning, created immediate industrial bottlenecks. Panther glacis plates required 82mm of face-hardened steel. Tiger frontal armor demanded 100mm. Tiger II specifications called for 150 to 185mm. The mathematics became brutal. Thicker plates required proportionally more alloying elements, more precise heat treatment, and longer production cycles. Molybdenum supplies collapsed first. Sweden, Germany's primary source, faced intensifying Allied pressure. By late 1942, molybdenum vanished from small and medium-thickness armor. By June 1944, it disappeared entirely from specifications, even for the heaviest plates protecting Tiger IIs. Nickel followed similar trajectories. Present in Tiger R by 1943 at 0.77 to 1.73%, it began vanishing from mid-thickness armor by mid-1944. Only plates exceeding 125mm retained nickel allocations through war's end. The substitute, vanadium, couldn't replicate molybdenum's performance. Meanwhile, Allied industry was perfecting a weapon that didn't care about armor thickness, the shaped charge. Swiss inventor Henry Mohaupt had demonstrated the principle before the war. Germans weaponized it first at Eben-Emmel Fortress in May 1940. By 1943, the Panzerschreck's 88mm warhead could defeat 200+ millimeters of rolled homogeneous armor. The future of tank warfare wasn't thicker steel. It was chemistry defeating metallurgy at the molecular level.
The physics seemed impossible. A hollow cone of copper, 2-3 millimeters thick, surrounded by high explosive. Detonate from the base. The explosive shock wave collapses the cone inward at velocities exceeding the speed of sound in copper. At the moment of convergence, the liner doesn't melt, it flows. Material scientists would later call this superplasticity under extreme compression. The result? A jet traveling at 7,000 to 10,000 meters per second. Faster than any rifle bullet. slower than orbital velocity, perfectly positioned to hydrodynamically defeat steel armor. German engineers at the Luftwaffe Weapons Institute in Braunschweig, led by Hubert Schardin and Franz Rudolf Tomanek, had solved the fundamental challenge by February 1938, achieving proper standoff distance. Too close, the jet hasn't fully formed. Too far, aerodynamic forces break the jet into fragments. The optimal distance, roughly 6 to 8 times the cone diameter, required precision fusing. By mid-1940, Germany fielded the first gun-fired heat round, the 7.5 centimeter Gra 38 HL/A for the Panzer IV's short-barreled KWK x37L x24. Penetration? 100 millimeters at any range, because velocity, the god of conventional ballistics, no longer mattered. Testing grounds at Kummersdorf documented the mechanics. Flash radiography captured line of collapse at 25 microsecond intervals. The copper jet appeared on X-ray film as a narrow needle extending forward from the explosive's detonation wave. Behind it, a slower-moving slug of residual liner material, called the carrot for its appearance, followed at roughly 1/10 the jet's velocity. Impact temperatures measured 500 to 800 degrees Celsius, not melting temperature for steel, just hot enough to matter. But the real violence came from pressure, 100 to 200 gigapascals at the penetration interface. At these pressures, metallurgical concepts like hardness and ductility became irrelevant. Armor steel behaved like fluid under extreme compression. The Popular Science headline in early 1945, "It makes steel flow like mud," wasn't hyperbole. It was hydrodynamics.
The first Panzerfaust, officially Faust Patrone Klein, arrived on the Eastern Front in October 1943. Infantry squads regarded the disposable tubes with skepticism. Effective range, 30 meters. A soldier needed to let a 45-ton T-34 approach to grenade-throwing distance, expose himself from cover, and squeeze the firing lever. The backblast extended 2 meters behind the operator, announcing his position to every Soviet rifleman in range. Survival odds looked poor. Then someone actually fired one. The 1.8-pound warhead, traveling at merely 30 meters per second, walking speed for a sprinting man, struck the T-34's 45mm side armor. The shaped charge detonated. 100 millimeters of penetration capability against armor barely 1/3 that thickness meant the copper jet passed completely through both walls of the crew compartment. Inside, catastrophic overpressure, metal fragments traveling at supersonic velocity, spalling from the interior armor surface, ammunition ignition. The Soviet crew didn't have time to bail out. German after-action reports from late 1943 documented the psychological impact. Infantry confidence in anti-tank capability increased dramatically. Tank crews reported the opposite phenomenon. Soviet armor became increasingly cautious in urban terrain and forests where standoff distances collapsed. By December 1943, monthly production reached 200,000 units. Demand exceeded supply by factors of 3. The Panzerschreck followed similar trajectories. Based on captured American bazookas from Tunisia, the 88mm RPG B-54 entered service with specialized anti-tank teams, 2-man crews, gunner, and loader. Effective range against moving targets, 100-120 meters according to German specifications. Finnish tests suggested actual combat performance closer to 100 meters. But that 100 meters delivered 200+ millimeters of penetration. Against a Sherman 76mm frontal armor, overkill by nearly 3 to 1. American tankers in Normandy began welding sandbags, spare tracks, even bed springs to their hulls. British trials at Shoeburyness determined the brutal truth. Effective standoff protection required roughly 1 meter of air gap. Sandbags provided maybe 15 centimeters. Mathematical futility, psychological necessity.
By spring 1944, German procurement officers faced an elegant horror. They'd created an infantry portable weapon that could kill any Allied tank, and they needed millions of them. The economics were obscene. A single Tiger II cost 800,000 Reichsmarks. Production time, 6 months from steel allocation to battlefield delivery. Crew training, 8 weeks minimum. The tank consumed 340 liters of fuel per 100 kilometers, fuel Germany increasingly lacked. A Panzerfaust cost 30 Reichsmarks. Production time, 4 hours. Training, 30 minutes. Fuel consumption, 0. Reichsminister Albert Speer's production planners recognized the strategic mathematics immediately. Manufacturing shifted from tank-centric anti-armor doctrine to distributed infantry capability. By April 1944, monthly Panzerfaust production exceeded 400,000 units. By October, 900,000. By February 1945, production peaked at 1.5 million monthly, enough to equip every surviving Wehrmacht infantry squad with dozens of disposable launchers. The doctrinal shift became visible in defensive preparations across Europe. German engineers constructed staggered trench systems 115 meters apart, slightly beyond Panzerfaust maximum effective range but close enough for coordinated ambushes. doctrine specified attacking tank formations from multiple angles simultaneously, targeting thinner side armor where 40-50 mm offered minimal protection against 100 mm penetration capability. Allied intelligence tracked the proliferation with mounting concern. Operations Research Office analysis of 12,140 knocked-out Allied tanks revealed the temporal pattern. In 1943, heat weapons accounted for less than 2% of tank casualties. By early 1944, 10%. Italy, spring 1945, 25%. Eastern Germany's urban combat zones, 70%. The statistics told a clear story. Tank guns still killed the most armor, 54% overall, but shape charges represented the steepest acceleration curve. Soviet response protocols evolved rapidly. Heavy tank companies in urban environments received dedicated infantry platoons. Their sole mission was protecting tanks from German infantry within 150-meter kill zones. American armor doctrine shifted toward combined arms operations, refusing to advance without infantry support in close terrain. The tactical revolution was complete. One man with a disposable tube could checkmate 40 tons of steel.
The Panzer Grenadier pressed his back against the cellar's brick wall, feeling vibration through the masonry before hearing the sound. Berlin, April 1945. Soviet IS-2 heavy tank, 46 tons. He couldn't see it yet, didn't need to. The grinding of steel tracks on cobblestones announced its approach through the smoke drifting across Invalidenstrasse. 70 meters, maybe 60. His hands found the Panzerfaust 100 by touch. Safety pin removed 2 minutes ago. Hands shaking despite 2 years combat experience. The psychological calculus was simple, terrible. He had to let the tank close to 40 meters for guaranteed effectiveness. Closer meant better penetration angles. Closer also meant the IS-2's hull machine gunner could see his firing position. The backblast would announce his location to every Soviet rifleman within a 100-meter radius. Fire and die, or die without firing. The turret's curved armor appeared through the window gap. Massive 122mm gun barrel traversing left. The tank wasn't hunting him. It didn't know he existed yet. Standard Soviet urban doctrine: fire high explosive rounds into building facades, collapse structures on defending infantry. 50 meters. He shifted position, braced the tube under his right arm, aligned the sight post with the tank's side hull. Thinner armor. Maybe 90 millimeters versus 120 frontal. The math worked. 40 meters. The tank stopped. Turret rotated toward his building. Decision made for him. He squeezed the firing lever. The hollow hump of propellant ignition. 2 meters of backblast. Scorching heat. Pressure wave hammering his eardrums. The warhead flew perfectly straight over 40 meters. Impossibly slow. Impossibly lethal. Impact. Orange flash at the hull turret junction. The shaped charge's copper jet penetrated in microseconds, a phenomenon his brain couldn't process in real time. What registered? Secondary explosion inside the crew compartment, ammunition cook-off, black smoke erupting from hatches. Silence. Then, rifle fire snapping through the window above his head. Soviet infantry had acquired his position. He dropped the spent tube, grabbed his car 98K, ran for the stairs. Survival. Unlikely. Mission. Accomplished.
The mathematics of shaped charge penetration defied conventional ballistics. Traditional armor-piercing rounds relied on kinetic energy equations. Penetration depth increased with projectile velocity, mass, and hardness. A 76mm M62 APC-BC round needed 700+ meters per second impact velocity to defeat 100 millimeters of armor. Slower impact meant failure. Heat rounds ignored velocity entirely. The mechanism operated purely through hydrodynamic pressure. When the copper jet, traveling at 7,000 to 10,000 meters per second, struck armor, impact pressures reached 100 to 200 gigapascals. For reference, atmospheric pressure is 0.0001 gigapascals. These pressures exceeded the dynamic yield strength of armor steel by factors of 10,000. At such pressures, solid materials behave as fluids. The jet doesn't melt through armor, Popular Science's 1945 headline notwithstanding. Jet temperatures measured only 500 to 800 degrees Celsius, well below steel's melting point of 1370 to 1530 degrees. Instead, the penetration occurred through a process material scientists termed hydrodynamic penetration. The armor material flowed outward from the impact point, displaced by extreme pressure rather than thermal effects. Penetration depth correlated directly with jet coherence. Flash radiography studies at Columbus revealed the jet stretched during flight, eventually breaking into discrete particles. High-quality warheads maintained coherence for 12 to 20 cone diameters of travel. Lower-quality designs fragmented at 6 to 8 diameters. This explains standoff sensitivity. Too close, insufficient jet formation. Too far, jet fragmentation. The copper liner itself followed precise parameters. Thickness, 2 to 3 millimeters for 88 millimeter warheads. Cone angle, typically 42 degrees, though experimental designs ranged from 30 to 60 degrees. Material purity mattered. Impurities caused jet instability. The Germans used oxygen-free copper when available, accepting slight performance degradation when forced to substitute. Spin presented catastrophic problems. Centrifugal force dispersed the jet, reducing penetration by 50 to 70%. This force shaped charges towards fin stabilization rather than rifled gun compatibility. The Germans solved this for tank guns through bearing-mounted driving bands that allowed unspun flight from rifled barrels. Engineering elegance, a solution that worked until Germany ran out of precision bearings. Like everything else in 1945.
Soviet tank crews developed superstitions about Panzerfausts. Rational men understood that 40 millimeters of side armor couldn't stop 100 millimeters of penetration. Mathematics was absolute. But the human brain resisted absolute vulnerability. So crews welded spare track links to hull sides, hung sandbags from turret skirts, bolted bed springs to frontal plates. None of it worked. All of it felt necessary. German Panzergrenadier Werner H., Battalion Records, 12th SS Panzer Division, described his first Panzerfaust engagement in a 1946 Allied interrogation. You know the tank sees you, you know their machine guns will fire, but you also know if you hit the ammunition, they burn. Fear in both directions. The psychological equation favored neither side. British tank crews in Normandy-Spokash terrain reported the highest stress levels measured during the entire Northwest European campaign, exceeding even direct artillery bombardment. Reason: inability to maintain standoff distance. Hedgerows limited visibility to 30-50 meters. Every corner, every intersection represented potential ambush range. Sherman Commander reports, U.S. 2nd Armored Division, Normandy Sector, documented behavioral changes. Crews refused to advance without infantry within visual range. Multiple incidents of crews abandoning operational vehicles after hearing nearby heat detonations, even without taking direct fire. The sound became diagnostic. Tank crews learned to distinguish shape-charge detonations from conventional high-explosive rounds. The heat signature, sharp metallic crack, minimal blast overpressure, followed by internal secondary explosions if penetration occurred. Veterans described it as hearing your death before it arrives. Israeli Defense Forces documented long-term patterns in Lebanon War Studies, 1982. 98% of tank crew burn casualties occurred despite wearing fireproof suits because facial protection remained inadequate. 77% sustained facial burns. Only 9% wearing fireproof gloves suffered hand burns versus 75% without protection. The lesson endured across decades. You could survive the initial penetration. The thermal aftermath killed you anyway. Shape charges didn't just defeat armor. They defeated the psychology of armored warfare.
By December 1944, Allied intelligence had captured enough Panzerfausts to conduct systematic testing. British proving grounds at Shoeburyness ran controlled trials with sobering results. A Panzerfaust 60 warhead defeated 100 mm armor plate angled at 30 degrees, even with an additional 5 mm screen placed 127 mm forward. Only Churchill 7's 152 mm frontal armor, struck at oblique angles, provided marginal protection. American tests quantified the standoff requirements precisely. A 6 mm plate positioned 28 centimeters from 76 mm base armor could protect against Panzerfaust 30. Against Panzerfaust 60, useless. Against Panzerschreck, a 20-inch, 51 cm standoff barely protected 100 mm plate. The mathematics condemned improvised armor to futility. Soviet countermeasures evolved through brutal empirical testing. Captured Panzerschrecks underwent reverse engineering at proving grounds near Moscow. Engineers determined that spaced armor worked if the gap exceeded 1 meter. Since adding 1 meter standoff plates to a T-34 was mechanically impossible, doctrine shifted toward tactical solutions: infantry screens in urban terrain, artillery suppression of defensive positions before armor advance, combined arms coordination. German intelligence, meanwhile, faced opposite problems, defending against their own weapons. Wehrmacht analysis of captured Allied heat munitions, primarily American bazookas and British Piat rounds, revealed comparative inadequacies. The bazooka 60 mm warhead penetrated roughly 100 mm versus Panzerschreck's 200+. Piat's spigot mortar delivery system caused inconsistent standoff distances, reducing penetration reliability. This intelligence produced false confidence. German technical superiority and shaped charges couldn't offset industrial collapse. By February 1945, Panzerfaust production required copper allocations competing with electrical wiring for Tiger II fire control systems and communications equipment.
Choices became binary: build 1,000 Panzerfausts or wire 50 tanks. The strategic calculus favored disposable weapons. American Postwar Analysis, Operations Research Office, 1946, documented the adaptation timeline through captured German documents. October 1944 Wehrmacht Tactical Directive specified Panzerfaust teams positioned in staggered positions 115 meters apart, targeting vehicle flanks from multiple angles simultaneously. It was combined arms doctrine inverted, infantry hunting armor instead of armor supporting infantry. The revolution was complete.
The final twist arrived in metallurgical reports, not battlefield accounts. When American engineers examined captured Panther glacis plates in January 1945, they discovered carbon content of 0.40 to 0.57%, nearly double the 0.30% maximum specification used in U.S. and British armor. The steel quality rating, D, borderline acceptable. Fracture analysis revealed extremely brittle nature with bright, flat, crystalline surface. The Germans hadn't just lost access to molybdenum and nickel. They'd lost metallurgical process control. Vanadium substitution required different quenching cycles, plates heated to 1200 to 1700 degrees Fahrenheit, then rapidly cooled. But factories rushing to meet Albert Speer's production quotas couldn't maintain proper timing. Improper quenching created internal stress fractures invisible to inspectors. Improper tempering induced brittleness throughout the plate structure. By second quarter 1944, over 30% of armor batches failed initial ballistic trials. 15% failed second trials, 8% failed third trials. Primary failure mode, spalling. When Soviet 122mm rounds struck late war Panthers and Tiger IIs, even non-penetrating hits, the armor failed catastrophically. Not from heat, not from kinetic energy exceeding design limits, from metallurgical brittleness causing massive internal fragmentation. The shape charge's thermal-mechanical violence found every microscopic flaw. Post-war, the technology proliferated globally. Soviet RPG-2 copied Panzerfaust 250 designs. Modern RPG-7s traced direct lineage to German wartime development. Contemporary tandem-charge heat warheads achieve 800mm penetration. But the metallurgical lesson endured: armor quality matters more than thickness. The shell that melted German tank armor never melted anything. It exploited fundamental material science. Copper jets traveling at hypersonic velocities, generating pressures that made solid steel flow like fluid, striking armor whose crystalline structure had been compromised by resource scarcity and production desperation. Industrial warfare's cruelest irony: Germany pioneered the weapon that exploited their own metallurgical collapse. Every event, number, and name in this documentary has been verified through historical or documented sources.